Hi, welcome to this lecture on binary search trees. My name is Dr. Ritesh Shujura. Before we can discuss binary search trees, there are a few concepts we need to go through first. The first is that of an ordered map. In an ordered map, keys come from a total order relation. You can think of an ordered map as increasing values in a contiguous array. So you've got an array, and arrays, remember, are contiguous access, and increasing keys would be perhaps an array of size 10 with the numbers from 1 to 10. So in increasing order, so the first cell will have 1, the second cell will have 2, the third cell will have 3, and so on. So in an ordered map like this, you can have several methods. The first method can be something like first entry, in which we return the smallest key. The first entry, the smallest key. Last entry will have the largest key in the map. We could also have methods that are with respect to an integer value, which we might call k. So k, if we pick in our running example from in the array that has the values from 1 to 10, 1 being the smallest key and 10 being the largest key, in a array of contiguous values, methods such as floor entry of k, let's say k is equal to 5, will return the largest key, which is less than or equal to k. Okay, and if we make it a bit tighter, if we just say the largest key smaller than k, in this case 5, then for our running example, for the array containing the values from 1 to 10, we would return 4, because 4 is the largest key that is smaller than 5. Similarly, we have this notion of a ceiling entry, and the ceiling entry with respect to k is the smallest key greater than k. So that will be, if k is 5 in our example, we would return 6. If we have the smallest key greater than k, let's suppose we don't allow for values that are also equal to k. We might have the case where our keys are unique, in which case we might not have any keys with the same value. And if that's a requirement of the data structure, then the floor entry definition would be of some particular value k will be the largest key, strictly less than k. And for the ceiling entry, it would be the smallest key, strictly greater than k. So this is just eliminating based on some rules based system. So it's not that bad to actually implement these few methods for an array for values from 1 to 10. So continuing with this notion of an ordered map, we find that we can implement several searching procedures in an ordered map. And one of the most famous of these search procedures are to find a particular key. So we want to find a key, suppose a key like 3 in an ordered map. We need a particular way to do it. So a way of doing this in an ordered map is by using a binary search. So binary search can perform operations get, and it can also perform a floor entry with respect to some k and ceiling entry with respect to some k on an ordered map implemented by the means of an array-based sequence. So when we speak about binary search, we speak about array-based implementations because it makes sense in an array-based implementation because the complexity is significantly reduced, as opposed to random access, things like linked lists. So if we have an array like this one, which has the value from 0 to up to 19, well, there are a few things that it skips, like 2 and a couple of other numbers, but you've got these integers. We have 0, 1, 3, 4, 5, 7, 8, 9, 11, 14, 16, 18, and 19. And you've got your lowest value, which is at the first, because it's an ordered map, there is an total order between the keys and it's sorted. So the first key is the smallest and the last key is the largest. From that, we can actually implement these kinds of methods: first entry, last entry, floor entry, and ceiling entry. And binary search allows us to implement this efficiently. So you can imagine if you didn't have a very sophisticated search procedure, you would just use the most basic kind. If I asked you to search for 7, then you would start at the beginning. You would say, is this value 7? No. 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 Is this value 7? Yes. So if you do that, in the worst case, your complexity would be O(n), because there are n things in this list. Well, that's a lot if you think about it, because that's as bad as it gets. There's n things and we're searching through n things. So in the worst case, we would have to go right to the end of the list. So this is a bad complexity, just searching through the list. Well, so seeing that if this was an unsorted sequence, that might be the only option to search in this way. But given that there is an order here, it's sorted and it's being preserved as a sorted sequence, when we add values in, it's inserted in the correct position, we could develop a more sophisticated way of doing this. And this serves as the motivation for what this lecture is actually about, which is binary search trees. But we've got to start here with binary search. So binary search is a really clever way of finding things in a sorted array-based sequence. Okay, and it has to be an array because you should be able to access anywhere in the array should be accessed in O1. If you can't access things in O1, binary search doesn't work. In fact, if you can't access things in O1, with indexes in O1, then binary search would even provide a higher computational burden. For example, if you're trying to implement a binary search in a linked list, and perhaps just using a normal search procedure, going element to element in a linked list, the element to element implementation will be cheaper than using binary search. So let's look at this binary search algorithm on this particular array. And you've got things arranged, the keys arranged in a contiguous way. And this is position M to indicate that this is an index. This would be index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So the way binary search works, very simply, and I'm sure most of you have seen this before, if we are searching for something like 7, we'll first look at the middle element. So the middle element is at the middle index. You would then find the middle index by looking, it's very easy. You just take the total size, the entire array, half it, and it'll take you to the middle. And you search there for 7. And you look there, and 7 is not there. So what do we do? Well, what we could do is simply, knowing that 7 is smaller than 8, we could just eliminate everything greater than 8. And we know everything greater than 8 is on the right-hand side of 8. So we simply eliminate from 8 onwards, and all of this gets scratched out in our search. It's as simple as that. What have we actually done at this step? We have the problem. We had a big list to search, n values, and then we halved it. So now we just have n/2 to search. Well, let's do the same thing. So you've got now exactly the same search procedure, but now with half of the total size. So that means we're going to be looking at this half. What do we do? Well, since this is our new array from 0 to 7, all I would need to do is just take the total size, divide by 2, and it'll give me the middle element. So that's where I go. If you're wondering about the cases where you have odd numbers or even numbers, you can just take the ceiling or the floor of the middle. So if, for example, if the middle is index 4.5, you just take the floor, which will give you index 4. So in this case, this is what we did. We took the floor. So great. So now we say, well, is 7 equal to this index? Is 7 this? Is 3 equal to 7? No, it's not. But we know that 7 is greater than 3, so it will belong on the right-hand side of 3. Since we already eliminated from 8 to 19, we don't even have to consider that. We will only consider 4, 5, and 7 in searching this. And what do we do again? We halve the problem. Again, we halve the problem. So we halve the problem. We eliminate all of these values, which are 3 is not equal to 7, and everything on the left-hand side is less than 7. So we can take them out. And we continue in this way. So now we've got a smaller list to search. So we halved this problem twice. And what are we left with? Something even smaller. So we find the middle value. It's 5. 5 is 5 equal to 7? No, it's not. So that means that we need to see 5 is greater than 7 or less than 7. We find that 7 is greater than 5, so we cannot be on the left hand side of 5. So we eliminate 4, which could have been a large array, but we eliminate it, and we're left with the right hand side. And once we find the middle element there, we end up finding 7, because 7 is equal to 7. This is a key that we're looking for. So this is how, if this is really the rationale behind what we'll be doing in this lecture, and it's called binary search trees. If you can imagine, we're just going to be looking at a more graphical representation of the search algorithm. So you're going to be seeing the search algorithm just in a more graphical way. When I say graphical, I mean with pictures. Here we were looking at this algorithm in terms of an array, but now we're going to look at this in terms of a tree. And we'll see, and you'll actually see the similarities or the motivation for binary trees motivated by binary search. Great. So search tables, let's complete this. So a search table is nothing more than an ordered map. We spoke about ordered maps, and it's implemented by a sorted sequence, like our example from 0 to 10. We store items in an array-based sequence, not random access, in contiguous access, sorted by key, and we use an external comparator for the keys. You can define this in any way you want. We're using a total order relation here. The performance varies, right? Okay, so if you use binary search, then in an ordered map, you can achieve get a particular key, find the floor of a particular key, find the ceiling of a particular key, all in log n. Why is this? Why is this? And I want you to think about that. We'll actually, I think when you see the tree, it'll be very obvious, and we'll come back to that. But using binary search, we will always get log n in the worst case. And I want you to think about that, because that's very important. And we'll actually look at examples, and hopefully I can convince you that that is true. So this is supposed to be put, not get. I think that's a mistake. So maybe I should write it here as put. Put takes on. And why is that? Why does put take on when everything else, get floor entry and get the ceiling entry and everything else, take log n? Well, because even though we can get the correct position to insert an item, we still, because we're dealing with an array, we still need to make space for that item. Okay, so let me just go back and show you. So this is from 0, 1, 3, 4. Suppose I am inserting 2. Okay, maybe something a bit more further up. Suppose I'm inserting 15. Then to find the correct position where I need to put 15 is easy. I would just use get, because that I can achieve in O log n. Okay, so I'll find the position where I need to put 15, which is between 14 and 16. But to actually insert 15 in there, that won't be straightforward. Okay, why is that? Because I've got to make space for this. Remember that everything is stored in contiguous memory. Everything is stored in an array. Okay, it's written here somewhere. Let me show you. It's all stored in an array-based sequence. Okay, arrays mean they're contiguous, which means that these items are sitting in memory next to each other. Which means that I would need to make space in memory to put the 15 in here. Which also means I would need to shift 19 to the next cell, shift 18 to the next cell, shift 16 to the next cell, then I can put 15 in here. So even though finding where 15 goes, finding where k goes is log n, but we still need to do shifts. We need to make room for it. So it'll be on. Erase is the same. Even though we know what to erase, we find it very quickly. We know where it is that needs to be, where the key is that needs to be erased. We still have to shift items into the place of the thing that we need to move out. So the same analogy, just for completeness, you have your list. I want to remove 7. Finding 7 is easy, log n time. We'll also remember, because this is binary search, whenever we speak about log n, we're always speaking about base 2. And this is true for the whole course. Okay, whenever, unlike in other courses where you just assume log base 10, in this course, data structures, and in the, well, for the most part in the undergraduate computer science curriculum, we always assume log base 2n. Always, log base 2, always. Unless otherwise told. Okay, fantastic. So erase takes on, because if you want to erase 7, you need to find 7 first, and then you can put 8 in 7's place, put 9 in 8's place, 11 in 9's place, 14 in 11's place, 16 in 14's place, 18 in 16's place, 19 in 18's place. I hope this makes sense. Okay, remember, if you are struggling with the coursework and you do need to ask a question, the teaching assistants are actually very responsive when you put things up, either in email to them or on Moodle. But post your questions and let's try to get to them as quick as we can. Okay, so what's the problem here? We've got search tables and they look really great. We can, because they're sorted, it's easy to find things. It's easy to find the floor of things and the ceiling of things. But putting things inside of it is ON, which is expensive. Erasing things from it is ON, which is expensive. And so if we have more frequent operations here than here, so more frequent gets, floor entries and ceiling entries, and less gets and erasers, then we can prefer to use search tables in this way with contiguous access. Right, so now that we have, so we had to go through all of these things to speak about binary search trees. So now that we've covered ordered maps and we've covered search tables, we now can finally move to binary search trees. So you remember what a tree is. Remember that a tree is a structure where each node has one and only one parent. That's the definition of a tree. A binary tree is one in which, well, if you remember from the previous lecture, it's a tree where every node has at most two children. You can have one, you can have none, you can have two, but you can't have three. Okay, so you can only have two children. What does that remind you of? So, binary trees, that's a concept. Trees, you've covered it. Binary trees, you've covered it. But binary search trees is what this lecture is about. So binary search trees have a very special ordering. And the ordering is as follows. So if you have a tree, a binary tree, we can only call it a binary search tree if it has this property. And this property simply says that if you have three nodes, okay, so let's say U, V, and W. So U will be, this will be U, this will be V, this will be W. I would love to write it in if I could. Let me see if I can. Nope, maybe this. Yes, that worked. Okay, and how do I close this? Okay. So this will be U, this will be V, and this will be W. Okay, so suppose you've got this U, V, and W, okay? So U is the left subtree, okay? So the left subtree of V, so this is U. V is the node, and W is the right subtree of V, so the right subtree of V, okay? Then you have that the key of U is smaller than or equal to the key of V, and the key of V is smaller than or equal to the key of W. Okay, so you've got this order relation. I hope this graphic makes sense. And we have this additional this comes from the definition of binary trees. External nodes do not store items, so they just hang there. Okay, but look, this definition varies from book to book. But the thing that doesn't vary from book to book is this notion of this relation between these nodes U, V, and W. Okay, your U is smaller than or equal to V, and your V is less than or equal to W. All right, and in the case where we're storing unique keys, then we will just have a tight restriction. U is less than V, and V is less than W. Okay, so, well, now I think you'll see why the retrieval is analogous to that of, or the get is analogous to that of binary search. You'll actually see how this search procedure works. So let's actually do an example here. Suppose you've got this binary search tree, and it has the property, because we know what the binary search tree property is, right? This is it. So suppose you've got this. We can find, I hope you all can see my screen. It looks like it's flashing. I don't know why. I suppose it's fine. So if you want to get 4, how does it work? Okay, we start off here. We're looking for 4. We start off at the root. We compare 4 with 6 because it's the root. Well, 4 is less than 6. So we throw away everything to the right of 6. 4 can't be there. 4 has to be here. So we compare 4 with the left subtree of 6. And 4 is not equal to 2. So we need to see, is it on the right, or is it on the left hand side of 2, or is it on the right hand side of 2? Well, since 4 is greater than 2, it is on the right hand side of 2. So we halve the problem again. Does this sound familiar? Have you seen this before? Do you remember what we were doing here when we were halving the problem all the time? We kept halving the problem. We kept halving the problem, narrowing down our search as we were looking for something. Yes, we can remember that. And that's where the motivation comes from. So when searching for 4, you would simply compare 4 node by node, going down the tree, never going back up, always going down the tree. And that's how you get items. So you can imagine now, how would you do the floor entry get, or the ceiling entry get? How would you do that with respect to some value? Well, think about it. So I want you to think about the complexity of retrieving something, of getting a value. So in this case 4, how many comparisons would we need to make? Suppose 4 was in the tree. How many comparisons would we need to make? Well, we would need to make h comparisons, where h is the height of the tree. But we note that sometimes you could have a tree that has different height on different branches. For example, you could have a tree like this. You could have a tree like this. You could have a tree like this. You see that not all, we might get a balanced tree, in which case your get method will be, let's say your get method, it'll be easy to find things, okay? Or it might be difficult. Like if you have this case, for example, look at this. Your root is here, then you move to the right. There's nothing on the left. Move to the right, move to the right. Suppose there were more things here. This is starting to look like a linked list. And in this case, in this linked list case, suppose the thing we're looking for is here. Then we would need to search from the root, going to the height of the tree. Not eliminating much, right? Because we still have all our work ahead of us. Every time we go right, the whole tree is on the right hand side. All the nodes on the right. So we're not really halving our problem in this case, as we were halving our problem over here. So if you try to draw this as a binary search tree, you'll find something quite interesting. Let's try to draw it as a binary search tree. Let's start with this 8. Okay, so I'm just gonna delete these things. Oh, I can't. Maybe I can erase. Oh, this is not helping. Just so we can see, I'd like to convince you that in a binary search, it's a lot easier, computational wise, to get items. Okay, so have a look at this. In binary search, when we were looking for things in a sorted list, what we had to do was, we started with 8. 8 was our root. Okay, then on the left hand side, there was 3, and on the right hand side there was 14. So 3 would have been here and 14 would have been here. On the right hand side of 3 there was 0. On the left hand side of 3 there was 5. On the right hand side of 14 you had 18. On the left hand side of 14, you had 9. On the right hand side of 9, you had 11. On the left hand side of 18, you had 16. On the right hand side you had 19. And you had 0. On the right hand side you had 1. On the left hand side you didn't have anything. Okay, I shouldn't have drawn it, but it's fine. On the right hand side, okay, so now let's do 5. Here you would have had 4, and on this side you would have had 7. So do you see what's happening here? This tree is balanced. Can you see it's balanced? So 9 doesn't have a left entry here, and nor did 0, right? But this row is full, this row is full, this row is full, and this row is full. Just it doesn't look like that because my drawing is so bad. But each layer is full. There are one nodes on the first layer. This has 2 nodes. Here there's 4. And here there's 1, 2, 3, 4, 5, 6. But it could have been 8, 7, 8. All right, doubling in size. So the reason that this was log n is because the height of the tree was log n. And in the worst case, you would be going from 8 maybe to 7, or maybe to 16, or maybe to 19. In the best case, you would just be going to 8, or maybe to 3, or maybe to 14. But the binary search tree, binary search in the worst case is log n, because we are simulating a search procedure with a hypothetical balance tree. That's what makes it log n. But there is no guarantee in binary search trees that we will have a balanced tree. That's my point. So here's a binary search tree with nodes like this. Let me see if I can just erase all of these things. Let me try to erase this. Oh, this doesn't work, eh? What a pain in the butt. How do you take it out? Okay, you can't. You just have to erase it like this. Okay, I hope I can, let me just make it nice. I know some students are very pedantic about these kinds of things. I used to be one of them, so I know. I think I'm still one of them. Okay, so in a binary search tree like this, you have 1 and 2, then 3, then 4, then 5. This is still a binary search tree. Okay, it follows the definition. All the definition says is that u must be less than or equal to v, and v must be less than or equal to w. This is for all of them. So if this is your v, this is your u, this is your w. If this is your v, this is your u, this is your w. If this is your v, this is your u, this is your w. Okay, and so on. So in this case, this is your v, your u is here, but there's nothing there, and this is your w. Okay, so I think you can see why this is a problem, because while you are actually searching for 5, you're not halving anything because there's nothing here. All right, so that's the big problem. So going down this tree is just like going down a linked list, and the complexity of searching in this binary search tree is log n. Not log n, is O n, and that's the problem. So scratch that. It's not log n. That's my point. It's not log n, it's O n. Okay, I hope I made my point. I probably said it a few times, but I just have to get it across because this is very important, right? So just to clarify, just because it's a binary search tree doesn't mean that we can always guarantee get to be log n. In the worst case, getting in a binary search tree is O n, not log n. Right. I'm glad I got it across. Now let's talk about insertion. So inserting into a binary search tree is super easy, and I'd like to show you in Paint. Paint, okay. So let's look at Paint, right? This is now Paint, and I'm going to insert a few things for you. So usually in the class, I would ask you to give me numbers, and I would insert it for you so you can see the patterns and things, but I'm going to just do it on Paint, and I'm going to make up numbers for myself. So let's say I first insert a 5. So 5, since there's nothing in the binary search tree, this will become our root. I'm drawing with my mouse, so please forgive me. I tried to order one of those trackpad thingies, but I don't think it's going to come on time. So here's the 5. I want to now put an 8 in. Well, the 8, since it's greater than 5, it'll go on the right-hand side of 5. Well, the right-hand side of 5. Okay. So then now I want to put a 6. Okay, so 6 is greater than 5, so it comes on the right hand side, but it's less than 8. So 6 will come on the left hand side of 8. Okay, well, let's put a 1 now. A 1 would go, compared to 5, it'll go on the left hand side of 5. That's where 1 goes. Now I'm going to put a 2. 2 is greater than 5. It's less, 2 is less, 2 is less than 5. Okay. Okay, so it goes on this side, but it's greater than 1. So it'll go on this side of 1. Let's put a 3. 3 is greater, 3 is less than 5, it's greater than 1, it's greater than 2. Does this make sense? Let's start afresh again. Let's insert the 10. So here's my 10. Alright, now let's insert the 2. Let's insert the 3. Let's insert the 1. Okay, I hope you're getting this. Let's start afresh again. Let's insert a 10. Let's insert a million. Oh, nuts. Let's insert a 50. Let's insert a 52. I hope this is making sense. Let's insert a 51. Okay, so 51 would come here because it's less than 100, greater than 50, less than 52. Okay, so the direction of these arrows are important, right? I don't need to tell you that. There are arrows here. I just omitted them. If you don't put arrows in there, someone might confuse this for a graph. It's not a graph, it's a tree. What makes this a tree is that every node has one and only one parent, at most. Graphs can have many parents, but we're not going to get into that now. We'll get into that next week. Okay, I hope this makes sense. This is inserting. So now that you know how to insert, that's great. Here they're inserting 5. Okay, so all you do is you compare 5 with 6. 5 is less than 6, comes on this side. 5 is greater than 2. 5 is greater than 4, so the 5 goes here. It would go here. Great, that's insertion. Now let's look at deletion. Okay, so deletion. Now deleting a node isn't difficult. I don't know why students get confused with this. There's nothing difficult about deletion. So to perform deletion, there's two kinds of deletions you can get. There's removing an external, okay? Removing externals are easy. Okay, so if you want to remove 1, well then remove 1, you're done. Remove 5, done. Remove 8, done. Okay, so removing externals are easy. Now there's another case. If in the case where, so you're removing an internal node, right? But the internal node has an external child. Okay. In the case of that, all you need to do is replace the non-external child with the k that you're trying to remove. Right? So in this is an example. So 4 has an external child, left child. So all it needs to do is just take the internal child and replace it with itself, and there we get rid of 4, like this. 4 is gone. Ta-da! You could also have the mirror effect of this, okay, like this. If I had another item here, a 7. Suppose I had a 7 here. Why is this highlighted? No idea. Okay, anyways. So 8 has a left child, 7, and 7 also has its own things. It's external and another external here. Then in this case, which is the mirror image of this, you would simply, because 8 has a right child, which is external, simply replace 8 with the left child. Okay? Piece of cake. Okay, so that's now in the case where you've got a left child. So then you just move up. In other words, you'll just be moving up the subtree here, which is really easy. Let's talk about the case, now the more interesting case. We're trying to remove something that doesn't have two external children. So here you've got something, you're removing 5 here, and here you've got a left child which is a subtree on its own, and you've got a right child which is also a subtree on its own. So what are you doing in this case? Well, it's not very obvious. If you look at it, you might rack your head about thinking what to replace 5 with, but a little bit of thought and another key thing you need to remember will make it very easy. So the key thing that you need to remember is that if you do you remember the lecture on tree traversals? And I showed you the in-order traversal. Well, if you do an in-order traversal on a binary search tree, you're going to get an ordered sequence. How cool is that? And you can actually verify that when we're done here, or pick any of the binary search trees in this lecture, do an in-order traversal, and you'll see that you get the numbers in order. For example, an in-order traversal of this will give you the numbers 1, 2, 3, 5, 6, 8, 9. An in-order traversal of this will give you the numbers, the keys, the sequence 1, 2, 5, 6, 8, 9. All right, so you can try it out anywhere and you'll always get it, provided it's a binary search tree. That might come in handy. So I said you need two things to figure this out. So the first is that, the in-order sequence, how to get the sequence in order. And the second is how to find the successor. We call it the successor. Right, so let's see. If I want to replace 1, I need to find a suitable value to replace it. If I need to replace 2, well, that's easy. It's external. We can just get rid of it. If I want to replace 3, well, this one's really something you haven't seen before. You've got now a child here that's not an external, a child here that's not an external. So what do I do in that case? Well, I need to find someone here to replace 3. That someone or that some key can be on this side or it can be on this side. I need to find it. So how do I find it? Well, remember the floor and ceiling functions that we learned about earlier? We can use it. So we find that the most suitable thing to replace 3 here is something from this side of the tree. Okay, hypothetically, you could also find something on this side. But we call that something on this side of the tree the successor. Who is the successor of 3? I feel like putting a crown on 3. 3 has died, and now you've got to find the replacement. So who's going to replace 3? Well, 3, we can't pick the highest, because if we pick the highest, we'd be violating some properties. What we need to do is pick, so suppose we use the highest, right? The highest here, the highest value here is a 9. If we replace this with a 9, then we got some big problems, because we've got some values here that are smaller than 9 that'll be on its right hand side. That's a big problem, right? So what we need to do is pick the smallest value, the smallest here, the ceiling, not the ceiling, well, the smallest key from all of these. So let's look at what do we mean by that? I think it's the floor. Where's the floor? Yeah, the floor entry. It's the largest key, which is small. No, so we're actually looking for the ceiling. It's the smallest key greater than k. Okay, so in this case, our k is 3. Okay, we're in the smallest one that's greater. So we've got many that are greater, but we're looking for the smallest. So we're looking for the ceiling. And in this case, 5 is the ceiling. So 5 is what we're going to replace this with. So how do we do that? Well, if we're going to remove 5 from this, then we need another procedure. Well, lucky for us that 5 since 5 appears in the in-order succession, which means that it comes after 3 in the in-order traversal, then it'll be very easy to find, because we just have to go right once and continuously go left until we find whatever the node is, the in-order successor. And once we do that, we find it and we just remove it using our remove external. We've seen this case before. If we're removing 5, it's easy. It has 2 externals, so we can just take it out. If it had 1 external, then we'll use this method to remove it and see 1 external. So we would just simply remove 5 and using its own using this above algorithm, deletion 1, I suppose you could call it that, this deletion, and then replace 3 with 5. That'll preserve the binary search tree property. I hope this makes sense. I tried to do it, explain it as slowly as I can. I know online learning is not the best, but if you have any questions, you can always post them. Okay, this is how we would do it. Now, the smarter one of you must be thinking, well, what about the predecessor? Can't I replace it with the predecessor? So we spoke about the successor, which is the in-order succession, right? What comes after 3 in the in-order traversal. But it's just as easy to replace it with the predecessor. what comes before 3 in an in-order succession. So that will be 2. So you could have replaced 3 with 2, or whatever was on the rightmost child here. So that will be the succession of 3. So that's something to keep in mind. Pick one. You don't have to implement both. Just pick one. Whichever one you pick, just make sure that you can actually implement it. It doesn't really matter. One way to implement it is to actually perform the in-order traversal. But more importantly, you want to find the position, because when you find the position of the key, then you can just perform the remove for that key and then replace it for the one that you're trying to replace. That's there's two deletions. I would say there's 3 deletion scenarios. Okay, the first is where you have where the key you're trying to remove has 2 externals. I would say that's the first. The second is when the key you're trying to remove has one external, which is like this. So in the case of 9, you just remove it, you throw it away, doesn't matter. In the case of 6, you follow this procedure, where you're simply taking the 5 and replacing the 6. In the case of this, where you have two internal children, you need to follow this procedure. Find the succession, find the successor or predecessor of your V, and then use that to replace V. I hope that makes sense. Now the last lecture slide here is about performance. Well, performance is something to think about, because as I said before, and I went on about this, I won't go on again about it so often. As I said before here, the searching time of a binary search tree, this is still a binary search tree, it's a BST. A binary search tree where it is not balanced, unlike others like this one where it is balanced. Or here in binary search where we hypothetically have a balanced tree. I say hypothetical because the structure, the balance structure is implicit. It's not explicit. So we have to draw it ourselves, right? So in the case like that, this is balanced. Here we can get O log n. Remember, every time it's base 2. Here we can't get log n, we'll get O n. So the performance of binary search depends on how the keys are inserted. If your keys are inserted from smallest key to largest key, then you will get this structure. If you are inserting keys from largest to smallest, you will get the other structure, this structure. And no matter, it really depends, right? I mean, like you can have, who knows how the keys are going to be inserted in, all right? You can have the case where keys are randomly, you're in control of how keys are inserted. In some cases, you are not in control of how keys are inserted. But the way the keys are inserted dictates the complexity or the performance of binary search tree. And that's a big problem because, like you say, things are very stochastic. You can't really say that my keys are going to be inserted in such a way that the resulting tree will be balanced. You cannot do that. Right, so to conclude this lecture, I would like to say that we have seen what binary search trees are made of. We have seen the complexity of binary search trees, but we have also seen a big problem with them. And the big problem is that the way the keys are inserted, the way the structure of the tree develops dictates the complexity of the tree. And that's a big problem. So we need a way to optimize on this. We need a way to keep our tree balanced such that we can always achieve log n for searching. And also perhaps for insertions and for deletions, but mostly for searching, because that's what we want. We want to always be able to search in log n. And that's what we intend to do in the next lecture. We address this problem by introducing another data structure called AVL trees. And AVL trees are always balanced. They have a mechanism to always keep the tree balanced. And it does this using several routine maintenance procedures, which we will talk about. But the main thing is that you understand what is the performance of binary search trees and why we need more sophisticated structures to help us keep our data in a way that we can allow for easy retrieval. Thank you.